Much said? Yeah? Okay, well, welcome to session number 2, everyone. We were supposed to have, I'll just come out here for a second. Thanks. Hi, I'm Kelsey Singer. I'm from the Southwest Research Institute, and I'll be your session chair for the next 3 talks because one of our talks is shifted to tomorrow. Charles Chambeau is shifted to tomorrow. So we do have a little bit of extra time in this session. So feel free to ask lots of questions. And keep in mind, I think it's nice to remember what Maria was mentioning about the goals for the workshop and the white paper. So as we're looking at the topics for this particular session, what are the knowledge gaps? What are interesting things to do for the future, both with modeling and observations, and anything else I'm forgetting out there. So yeah, keep those in mind. And then we have a longer dedicated discussion period at the end of these 3 talks for these topics. So yeah, keep those things in mind and bring them up then, and we'll make a list to make sure we include those in the paper. Okay, so with that, we will go on to Rosita, and I apologize if I don't get your last name quite right. Kokotanekova. And she'll be talking, thank you. Okay, she'll be talking about evolution of comet nuclei from ground photometric observations, as you can see there. All right, go for it.
Yeah, if we can directly go to the next slide, that will be a short one. I'll be talking mainly about Jupiter family comets in this talk, but towards the end, I promise that I'll transition to centaurs. So the idea is to tell you what is the progress that we've made in the past years with ground observations to study the physical properties of JFCs and their surface properties as well. And the idea is to plan how we can use the same methods in the coming years to study more in the direction of centaurs. So if we go to the next slide, we'll see what we mainly do. So the photometric observations, they allow us to study the rotational properties of JFCs. If we observe the nuclei when they're hopefully inactive away from the sun, we can trace their brightness variation, which can eventually lead to us deriving the rotation rate as well as the elongation of the nuclei. Is everything okay?
Yes, I was just passing the clicker to Gal, who's better positioned to point it at the computer. But yeah, we can hear you, so we're good.
Okay. Yes, so we use photometric time series to study the rotation rates. And on the next slide, I have summarized that we can also use photometric time series to study the surface properties of the nuclei. So if we collect time series at different phase angles, we can derive the phase function slopes of the nuclei. And also if we have previous knowledge about the sizes of the objects, we can also derive the geometrical betas. So on the next slide, I've summarized that even though these are really straightforward methods in theory, in practice, they're very challenging because getting these observational data sets, first of all, is challenging to get the time. Second of all, their analysis is not so straightforward. So despite the efforts of the overall number of 300 Jupiter family comets, less than 40 have light curves well constrained, and even fewer have their surface properties studied. And the reason why we were able to improve this in the past years is mainly because we developed a method that uses photometric standard stars from all sky surveys on each frame, which makes our calibrations very precise, which allows us to derive the light curves and the phase functions from very sparse observations, in which way we save a lot of observing time, but we still derive precise light curves and precise phase functions. So with this in mind, we go to the interesting part of the talk, where the next question is on the next slide is, what can we learn from the light curves that we derive? So can you go to the next slide and then quickly jump to the one after that? Yeah, so that's the question. And then The first step that we can do is once we collect the light curves and the rotation rates of many objects, we can try to see what we can learn about their physical properties. So in this plot, we have the rotation period of all Jupiter family comets with non-rotation periods, either from previous observations, which is the gray points, the orange ones, which are from our work, and the blue ones, which are from spacecraft. So the rotation period is plotted versus the elongation. And if we model this population as consisting of rotating ellipsoids that are held together just by gravity, we can plot the curves, the diagonal curves, which show us what is the minimum density required to keep them together so that they don't get disintegrated due to fast rotation. And if we ignore the 322P, which is most likely an asteroid, and 73P, which we know is a disintegrating comet, we see that none of the currently known Jupiter family comets require densities larger than 0.5 grams per cubic centimeter, which is an excellent agreement with the measurement in situ from Rosetta, which says that the measurement on 67P is representative for the whole population. So this is what we can do by taking the whole sample of JFCs, and we can actually study the bulk properties of the whole population. And on the next slide, we have an even more interesting attempt to study the bulk properties of comets. So here we have the rotation period plotted versus the size of the object. And as you can see in the lower right part of the plot, we don't have any comets. So we don't have any large comets that are rotating fast. And we can explain this by not so complicated models where we model the nuclei as rotating ellipsoids that are held together by gravity and tensile strength. So by using the values for density from 67P and representative elongations for the ellipsoids, we have derived that the minimum tensile strength, bulk tensile strength required to keep these comets together is about 10 pascals, which is a very low value, but it's in great agreement with local measurements of the tensile strength on the surface of 67P, and also in very good agreement with studies of other comets, most prominently Shoemaker-Levy 9. So again, with just ground observations and studying the whole population, we're able to derive a very important bulk property that's in agreement with other studies. So the next slide has the next important question, which is what can ground observation tell us about the surfaces of small bodies? And if you go to the next slide, you'll see something very interesting that we noticed a couple of years ago. So with our work, we were able to double the number of comets that have their albedos and phase function slopes known. And we saw this interesting trend that objects that have slightly brighter surfaces also have steeper phase functions. Now, a disclaimer here is that many of these measurements have large error bars. And also for people who have dealt with phase functions, it's usually very important to probe the same range of phase angles if you're trying to derive a linear phase function. But unfortunately, since the observations are so challenging to obtain, that's not possible. So generally, these are slopes derived for the range between 3 to 20 degrees, but they're different for the different object. But if we believe this trend, and if we believe that it's not an effect of some measurements errors, then we should try to explain it. And the way we try to explain it is the following. So we think that dynamically younger Jupiter family comet nuclei start in the top right, where 67P and 81P are. And then progressively with time, they move down this plot and they end up in the lower left part where they have lower albedos and less steep phase functions. And in the following slides, I'll explain why we believe this idea, and I'll try to clarify what we mean by this evolutionary trend. So if you go to the next slide, yeah, the one, yes. So here on the right, we see a study by Vincent et al. From 2017 based on in situ observations of 4 comets visited by spacecraft, where they studied the cliff height distribution. So what this study showed is that that comets like 81P and 67P have surfaces dominated by steep cliffs, and also by they have those characteristic pits that were discussed a lot on 67P. While Hartley 2, for example, has a surface that's covered by dust and smaller particles. And there the characteristic pits cannot be found to be so prominent. So what they claim is that this is a trend in the surface evolution of comets, where dynamically young objects start with surfaces dominated by steep cliffs, and they get eroded with the longer time they spend in the inner solar system, they get eroded down to surfaces dominated by dust. So on the next slide, we have the dynamical study which confirms this, that indeed 81P spend much less time in the inner solar system than Hartley 2. And with this study, they claim that JFCs that are dynamically young indeed have those primordially looking surfaces. So on the next slide, I'm trying to prove the point that it is possible that these signatures that are seen in situ could also be seen from ground observations. So when the surface properties, the surface photometric properties of 67P were compared to the other comets, and also different areas that are considered to be evolved in more or less on 67P. So these comparisons show that indeed the different morphologies have different photometric signatures. And we believe that they could also be detected from the Earth, not just from in situ measurements. And the final argument for our evolutionary hypothesis is on the next slide, where we have the almost dormant comets down in the lower left part of the plot, where we see 162P, 10P, and 28P. And we believe that these are the comets that have spent the longest in the inner solar system. They're almost at the end stages of their cometary activity, and they have already been reduced to mostly covered by dust. So the final summary of this hypothesis is on the next slide, where we have plots from J.B. Vincent, who's illustrated what he believes and what our surface study shows is that Jupiter family comets might start with this structure that has deep pits and steep cliffs, and they gradually get eroded to objects that have much smoother surfaces. And as this happens, an object, so progressively it will have shallower and shallower pits. And as this happens, then it will produce less and less shadowing at large phase angles, which is what we think causes the phase function slopes to become more and more shallow with evolution. As for why the albedo will decrease with time, the simplest explanation would be that as a comet becomes more and more evolved, the volatiles from the surface, the ices, they will decrease, which will make the surface darker. But of course, all of this is still in the beginning, and we need many more observations to show this, many more studies, even lab work, to show whether this is really possible. But if this hypothesis is correct, then is it possible to check what centaurs look like, whether they have those deep pits as well? And if we move to the next slide, I've plotted my ideas of what we could discuss in the coming minutes, hours, or days. So the first question would be, can we somehow connect the morphology of what we think are primitive Jupiter family comet nuclei to centaurs? And if we can, and if we find pits, and even in the future, any signatures of layering in the centaur population, then does it happen at this stage? Are these structures caused by the violent activity as an object is entering closer and closer to the inner solar system? And then the next question would be, since we have observed contact binaries in the Kuiper belt, and we have observed contact binaries in many of the comets visited by spacecraft, we should try to look for more of them in the Centaur population and see how they evolve there with the very violent activity that some centaurs undergo. And the final point that I included there is whether we can study with ground observations the differences between active and inactive centaurs to see how this transition happens or why it doesn't happen for some objects and so on. And if you give me a couple of minutes, we can go to the next slide where I've summarized a program that we have been doing. So if we try to do this work and we try to do observations of centaurs the way that we have done it for JFCs, it will pose a lot of challenges. And we've experienced that from firsthand, because in the past few years we had a long program on a 4-meter telescope in Chile where we tried to get the light curves and surface properties of 35 KBOs and centaurs. So about, I think 5 or 6 of these objects are centaurs. And this program proved to be really challenging because of the faintness of the objects and because of the difficulty of scheduling the observations. So we were able to derive light curves and phase functions of these objects, but in the process, we learned a lot of lessons. So if anyone is interested in working on a large program to observe photometrically centaurs from the ground, we'll be really happy to share our experience. And the next slide shows an example of how our light curves and phase functions look like. Those are some of the best ones. Many of them are with lower quality. So if anyone is interested in working on such a program, it would be very helpful, I think, to share our experiences of how difficult it was and what one can learn from such a program. But on a positive note, I think it's possible in the next years. We will definitely work towards getting more and more of these objects analyzed for light curves and for surface properties. And we hope that we'll be able to connect the 3 populations in the scattered disk and centaurs and then Jupiter family comets. And that's all. Thank you.
Can you hear us now?
Yep.
Okay, great. There is a mute button on this microphone, just for everyone's knowledge. Great, thank you. That was a really good summary, and thanks for sharing the work you've been doing and also offering to share observation strategies. Questions?
Hi, I'm Julie Brousset from Florida Space Institute. In the plots you showed, there seems to be a trend with size also. So would you think that only large comets would survive to the stage where they become inactive, and that any smaller bodies would then maybe split and go back to the top left corner of your plot?
That is something that we actually discussed when we showed this plot. So one of the reasons why we think that there are large objects in the bottom, that is slide 16 if you want to go back. Yes, so the large ones are in the bottom, possibly because they have indeed preferentially survived, but there is also one small one. So not only the 137P is the small yellow one there. So not only the large ones survive, but the large ones probably preferentially survive. One of the reasons could be that they don't spin up so easily. Another reason would be that they have an effective mechanism to stop the activity before it becomes destructive. But I think it's a very interesting idea to think what would happen if they split and then we expose a fresh surface. Would they go back to the top? That's an interesting idea that I haven't thought about in this way.
Hi, Jan Fernandez from UCF. Hi, Rosita. This was a really nice talk. I did want to ask about the same plot. Actually, I'll ask a question that someone asked me, and I didn't really have a good answer. So I guess traditionally, probably people in here will correct me if I'm wrong, but traditionally, I guess the trend with asteroids was that as you go down in albedo, the phase darkening is steeper.
Yeah.
But this is the opposite. This goes the opposite trend. So do you have a comment about that?
I actually do. So if you go to my last slide, I have plotted I have shown an orange line which shows the trend for asteroids. So the orange line is the trend for comets versus what's known for asteroids. So the asteroids that we have observed are generally larger. So we're not probing the same population. Also, we haven't really probed asteroids of exactly the same range of albedos. They're brighter. But what I think could be happening is asteroids don't really get their surfaces processed by activity. So if you have craters, the craters will produce shadowing and steep phase functions for all of the objects, while for comets, the shadowing will decrease with the trend to the left. So the way I explain it to myself is that the craters should produce shadowing and they should produce steep phase functions. However, we don't find objects that have shallow phase functions because of this, because their surfaces don't get reprocessed.
Kelsey Reed, UCF. Thank you, Rosita. It's great, a great talk. I have a question about the same figure, mostly. While I understand the bottom left grouping, maybe I'm mistaken, but I was under the impression that 103P is a young JFC in terms of its level and nature of activity, and so I'm not sure if I really understand the trend in the middle part, you know, where 81P, 103P, 9P all reside. It seems like there's a bit of a mix there.
I think Jordan will give you the answer of that. So dynamically, it's.
Sorry, we're laughing because he's raising his hand very high.
Yeah.
Thanks. Yeah, so the argument would be that the reason 103P is thought to be old is that it's really flat. And doesn't matter how you spin it up or spin it down, it's a remarkably flat object. But the thought is, and I'm biased because I had a paper on this, that in the recent past, there's one region where if you spin up 103P, it actually undergoes a massive mass wasting event that can expose underlying ices. And so the overall shape of the body can be very old and highly evolved, but the activity itself can actually be very recently exposed. So the idea being that even though it's really flat, it's not prone to processes that can maintain activity, mass wasting events and whatnot. But it could be in sort of this episodic regime where once in a while you can actually get this massive event that can reactivate a section of it. And so it looks very active and very new, even though the body is also very old.
Okay, I understand. But at that scale, wouldn't the effects of shape, lobe composition, etc., kind of mask the small differences in dynamical lifetime that we get? Because for almost all Jupiter family comets, if you just integrate them back, they all roughly have a similar dynamical lifetime. They meet Jupiter, and then everything goes haywire.
Really should have two mics, or I should just sit next to Gail. Yeah. So, well, yeah. Okay. Yeah. So on dynamical lifetimes, we can say that this is kind of chaotic. When I say that this activity is recent, we're talking like 1986 to 1990s. So this is just a few apparitions in the past is when this activity may have been activated. And so on those time scales, we're not even looking at secular evolution. We're just looking at when could this have happened. And if it is really young, then Hartley 2 actually presents a really unique case where we can actually see young activity on an otherwise very old body. So we're looking at very short timescales in this case.
Yeah. All right. So we're gonna actually take a quick break, and then when we return, so we'll do a 10-minute break, Gal. 10 minutes. Yes. Thank you, Rosita. And for those of you in the room and online, we're gonna take a 10-minute break, and then we'll return to Matthew Knight's talk. 10:40.
in the near term and the longer term. And I've actually interspersed questions that I had throughout the talk rather than all in the last slide, but I've put them in blue boxes. So hopefully people will pick up on those. So first, Luke already covered this, but I just wanted to be straightforward on what my definition was. I was using the definition from Jewett 2009, which was perihelion and semi-major axis between Jupiter and Neptune, and not in one-to-one mean motion resonances with any planets. I actually pulled some numbers from Horizons, and they had a flag, I could say not Jupiter Trojans, but they didn't have flags for the other planet Trojans. So some of the one-to-one resonances with outer planets may have snuck in, but as with Luke's, it's going to be a small number of differences. And that was actually my first suggested discussion topic, is what should the optimal definition be, so we can keep that in mind for further discussion. And Rosita already introduced this nicely, and in fact, as I suspected, you've already seen her figure on the right-hand side. But just to make sure everybody's on the same page, in the past, we've learned a lot about the internal structures and properties of asteroids and comets by simply collecting large numbers of rotation periods of these objects. So first, with the asteroid population, it became evident there was this so-called spin barrier, that you did not see fast rotating large objects, and you did see fast rotating small objects. And from that, we concluded that small asteroids that were rotating fast were probably monoliths, and larger asteroids were rubble piles. And with comets, as Rosita already nicely explained, we didn't see anything that have, apparently with densities larger than around 0.6 grams per cubic centimeter, which the densities are on the right-hand side, but they're almost cut off. So again, we were able to infer that comets were low density before we actually had those density measurements from missions. So I wondered where we stand as far as centaurs go for this. So I went to Horizons and I pulled what properties I could find. It sounds like Rosita actually can now up these numbers by a fair bit. But what I found was fewer than 20 objects that we had rotation periods for. And again, at least this is what Horizons had in their database. So I plotted rotation period against diameter on the left, and then rotation period against peak to trough amplitude, which I got from the Brian Warner's asteroid light curve database. And at least to my eye, there don't seem to be any obvious trends in the data yet. Yeah, like I said, Rosita may have some more information, and there may be other stuff that's unpublished that's just not already in the Horizons, but this is what I could quickly find, that there are fewer than 20 objects for which we know all this information. So, whoa, those are totally different colors. All right, that was a red plot on my computer. So I started thinking about what is theoretically doable, and Rosita already kind of talked about this, but you'll see my thoughts on this. I plotted what I'm calling the theoretical best magnitude. So I took the H magnitudes and I said, what if these things were at perihelion while they're also at opposition and at zero phase angle? So basically, what is the brightest these things might ever be? That's obviously not the typical brightness or the brightness at any one time, but at the best chance, what could we do? So first I thought about if you had a 1 meter telescope with sort of some reasonable assumptions about what an amplitude might be, which I assumed at about a 0.1 magnitude amplitude. A light curve, so something that's fairly round, how would we be sensitive to it? And things to the left of the dashed line, I think we could probably get with the 1 meter telescope under ideal conditions. So you're talking something like 60 objects. So probably 2 to 3 times as many objects as we already know today. If you go to a 4 meter telescope, now you can do a fair bit better. With today's knowledge, probably something like 180 objects. I don't know how complete we are starting at around 22nd magnitude since this distribution turns over. But theoretically, I think 4 meters is about the biggest size telescope where you could hope to get tons of time to really go after this population if you wanted to do a big survey like Rosita was just talking about. But then if you get really optimistic and say, well, maybe we could do this with 8 meter telescopes. At the moment, we know of 220 objects, but I'm sure that there are many more objects out there. At this point, once you start getting this faint, there are many more objects that you could do that exist. We just don't know about them yet. So in the LSST era, this may change. But at that point, well, I've been scaling. So I was saying basically how faint can you get in 900 seconds? So an 8 meter, I was saying you could get to say something like 23rd. You're saying I'm off on my signal to noise calculations?
No, I'm just saying LSST exposures will be 45 seconds.
Oh, that's true.
So
yeah. So you can't go as faint as that.
Yeah,
reliable
I mean, if you had
at that.
Control of the LSST, you could do that.
Yeah.
Yeah. So
Good, yeah, good point.
So it might be more like your 4 meter.
Okay. I didn't think about that. Yes.
So wait, just to clarify for everyone and myself. So what Henry's saying is that the. Sorry.
You want to try to use just continue the summary, or would you mess that? Thank you.
Sorry, just to clarify for myself what you guys were just saying. So in this kind of approach, there's no real difference between having it on a 4 meter and the 8 meter telescope using the LSST cadence.
Right, because so I'm assuming that you could have 900-second integrations for these numbers. I mean, these are rough, right. But Henry's pointing out that LSST is not going to have 900-second integrations. It's going to be more like 45 seconds. So if you could have an 8 meter with 900-second integrations, you could go where I've put the line.
Okay.
And there's a hand up in the back.
Daniel Stern, JPL, but I think the idea is LSST finds them, but they'll have bigger than 0.01 mag uncertainties, and then you go back with an 8 meter, and then you can get them and do the light curves and everything. So I think you're right. Other than I think 23rd is pretty conservative for an 8 meter.
Okay, even with 0.01 mag uncertainties? Okay.
I'm used to 10 meter.
So. Wow. That was a drop the mic.
Okay.
All right.
I'll just add, I'll kind of find the middle ground. Yeah, so I think the difference will be between using LSST data. Sorry, this is Henry Shea, PSI. The difference will be doing a targeted survey using versus LSST data mining. So yeah, so if you do
All right, so just some caveats to what I was just talking about here. As I said, these were best case scenario observations. If there is coma, so if these things are active, that's going to suppress the light curve amplitude. That's not to say we can't detect it, but you may need a larger amplitude brightness variation of the nucleus if there's significant coma there contributing to the brightness. Also, something to think about is that because the viewing geometry changes of an elongated object, you might look at it at one epoch and see large amplitude, and a different epoch see a small amplitude. The example I found when I was looking at this was 54598 Bianor, which I don't know how you pronounce that, but which had a max amplitude of 0.75 in 2001, down to 0.34 in 2003, and around 0.1 in 2014 and 2016. So you're talking timescales 10, 15, maybe more years than that you have to be paying attention to try and get your optimal brightness on these things. An interesting thing I thought of when I started thinking about this was the selection bias against slow rotators. So I'm familiar with the selection bias that if the rotation period is longer than what you can do in a night, or twice what you can do in a night, then you're probably not going to be that sensitive. But in fact, LSST will be hitting things every 3 nights. So LSST may actually be sensitive to objects that have rotation periods that are quite long, like weeks kind of timescales, because then it will survey it with a reasonably good frequency. But if they have something like a period of 3 or 4 days, LSST may not be sampling that particularly well. So we may end up understanding short rotation periods and very long rotation periods, but have a gap in the middle there we need to be mindful of. And as we just started talking about with LSST, we're probably not going to get tons of time on 8 meter telescopes, at least at the moment. But we've already had some of the discussion I put for this last bullet point, but also see Mike Kelly's talk tomorrow for more on what LSST will do for this. So the other thing I thought about was, what about using coma morphology? And this is something, if you know my normal work on active comets, I do a lot looking at the gas in comets. So the pros, and this is an animation of a gas jet rotating around. The pros for this approach are that observations can be more sparsely sampled than light curves, and you get larger spatial scales, so you don't actually take as much of a hit by going to smaller telescopes than you do for bigger telescopes. But the con is that it usually works better with gas, and therefore it needs to be really bright because you're using narrowband filters. And at something like 12th magnitude on a 4 meter, effectively the only Centaur that this is going to help us with is Schwarzmann-Bachmann 1. And then I also actually don't know, and hopefully this will come up in some discussions, if Centaurs even have detectable quantities of the relevant gases here, CN in particular, or OH, or C2 or C3. So be happy to talk about that more. But centaurs, at least some centaurs, do have outbursts. So Charles will talk a lot more about this tomorrow, I presume. But he has found, and others have found with Schwarzmann-Bachmann 1 that have outbursts of sort of 3 to 5 magnitudes. Quite often, here's a plot from Yoshida. You see this about once a year or so. It has big outbursts. And the dust features, which you can see in the bottom row here, these dust features are visible for a number of days, and they change sort of on a day-to-day cadence. Oops, I did something bad. Sorry about that. I don't even know what I hit. There we go. Sorry about that. So at least in the case of Schwarzmann-Bachmann 1, high quality data is possible to get with 2-meter class telescopes, and you only really have to sample it nightly to be studying it. We think Schwarzmann-Bachmann 1 has a long rotation period though, so you might not be able to do this for all centaurs. But so my idea for this, I'm just sort of throwing out, is to monitor for outbursts and then selectively deploy key assets. So in particular, I've noted that currently surveys like ZTF are sensitive down to magnitude 20 or 21. That's a ZTF detection of outbursts by Echeclus in late 2017 on the right. And soon LSST will be sensitive to, I don't know, 24th, 25th magnitude for these sorts of outbursts. So my idea is simply, if we see outbursts, then we can follow them up and try and study them more clearly when we know there's gas material there, and that might help us to study composition. But this brings up a second discussion topic, and it's really a series of questions here, but I don't think we know how common the outbursts are. We don't know if there are differences between comet outbursts and centaur outbursts. And also, I don't think we know if the outburst material is reflective of the bulk composition or not. So my thoughts on following up are that we can deploy, like I said, the key assets. So we can do spectroscopy or narrowband imaging to look for gas compositions, or maybe with the narrowband imaging, maybe look for these sort of jet features like I was mentioning for comets. If the activity persists for, say, a few days, you might be able to see a jet spiraling around or rotating around or something like that, that would give you information about what the nucleus is doing. It probably requires 8-meter, 10-meter class telescopes. I didn't actually check the numbers, but it's certainly going to be beyond a 4-meter. I think probably this doesn't need to be as rapid of a follow-up as comet outbursts, because the lifetimes of the gas species are going to be much longer at 5 AU or more than they are at 1 AU. But you still have to think about the expansion velocity, that the gas is going to move out of your pixels, or the column depth is going to decrease too much. But I think it does give you a bit more flexibility on this. And the other easier thing to do is going to be broadband imaging for the dust coma evolution. For the brighter outbursts, this might well be doable on sort of 4-meter class or smaller, which again are the assets that I think we can get quite a bit of time on. One thing that's potentially interesting is something like Las Cumbres Observatory, where they have a global network of 1- and 2-meter telescopes. So in theory, if something's bright enough, you could continuously monitor it for 24, 48 hours or whatever. Again, if it's accessible at that size telescope. And so this is my last slide, which was just thinking about future possibilities. And this is the pie in the sky world where they're going to give us all the time we want on James Webb or on 30-meter class telescopes here, which is another discussion topic of what might we do with a very large time allocation on these sorts of things. So just point out the quick things I thought of in putting this talk together. For James Webb, that centaurs are sufficiently far away that tracking rates aren't a problem. That's a relief for me as somebody who's normally interested in stuff at 1 AU, and it's really hard to do anything with James Webb at 1 AU. So I was thinking, well, maybe we could look at comomorphology in CO and CO2. I know Mike Kelly's work, I think Gerbs has done this as well, pulling out CO and CO2, or evidence that there's gas in the longer wavelength filter with Spitzer, that there clearly are jets that are detectable in comets in those species. So maybe you can do this with James Webb with centaurs. Again, it's going to be challenging, but I'm asking for the sky here. Why not? I think that outbursts with James Webb is going to be tough because the target of opportunity timescales will be challenging. I don't think James Webb will be able to react fast enough to do this. So you'd really have to just target objects. On the flip side, I think that the 30-meter telescope ground-based assets would be good for target of opportunity follow-ups. They should have fast reaction times. Their access to shorter wavelengths than James Webb. In particular, the ground-based broadband imaging, I think should be really good with the very high resolution that's now capable from the ground. You could get look at the inner coma in dust jets in a way that we're not capable of doing today, and maybe you can suss out rotation periods that way. And maybe things like using an IFU or narrowband filters to go for something like CN, or if these telescopes have the sensitivity at 3,000 angstroms to go down to OH. So these are the sorts of things that maybe we could do in a perfect world where we get tons of time. But the techniques I see as the way to really pull out some of these numbers for a lot of centaurs. And that's all.
Great. Thank you. Yeah, so we have time for a couple of quick questions on this one. And then we also have a larger discussion time after George gives his talk, although it's on a slightly different subject. So that's why I want to have some questions for Matthew or comments, either way.
It's a comment.
Okay. See, it said comments and everyone raised their hands.
Hello, it's Rodrigo Leiva from Surrey. Yeah, it's a comment about the detectability of the light curve, the amplitude. Actually, there is an extra things here that the centaurs are close enough that the aspect respect to the Earth change in human scales. So actually detecting several times the amplitude, or not detecting the amplitude and then detecting the amplitude. Mm-hmm. That gives you an extra clue about the shape also.
Yeah.
This is what we did with charcoal, for example, and combined with other techniques to get the shape. So actually, we should try to get several times, if we are greedy, several times trying to get the amplitude and the rotation period.
Yeah, absolutely.
Yeah, there's one in back here.
Alan, you can go first. Yeah, this is probably obvious, but I didn't hear it said. But I think one very productive thing to do would be to set up a burst alert project from LSST, and then have guaranteed short notice call-up time for other support telescopes to do just this kind of burst work with spectroscopy and imaging. Mm-hmm.
Yeah, so I don't know if Mike or Henry are going to talk about this at some point this week, but I know at least a bunch of people in the small bodies community have been working with LSST folks to plan these sorts of things. What triggers would we want in place to notify people that an object's brightness has changed?
Actually, along those same lines, it might be worth it as an outcome from all of this to consider maybe leveraging some of the ground-based monitoring campaign capability, which you are well aware of, that we've just been deploying for the HMP, TGK, and Vertinen campaign. Because if we can bring in the amateur community, that's where most of these outbursts are getting detected anyway. That might help with activating TOO programs and otherwise with the Centaurs. And then one thing that you should really think about putting on this future possibilities is, at least we hope, that there will be a NeoCam. Mm-hmm. And if there's a NeoCam, that will really totally blow open our ability to look at these objects and look for outburst activity, which is something you could say more about if you want. Sure. There you go.
Yeah, can you give us a 30-second summary of what capabilities for NeoCam might be?
So NeoCam will actually be able to, it'll constrain, so the cadence, it's all kind of constrained by the cadence, but it will be able to detect down to kilometer size objects in the inner Centaur region, that is inward of not out to basically Saturn distances. So the other, and it will also have a CO and CO2 combined channel, similar to what is now there with NEO-Eyes. The dwell time is longer, so the sensitivity in terms of the detection of CO and CO2 are also going to be improved. So, but But there, again, there remains no way of differentiating between CO and CO2.
Great. All right, I think we should go on to Jordan's talk. And remember that we have the discussion period at the end of this, so please, if you have more questions related to Matthew's talk, we can bring them up then. Let's thank Matthew one more time. Especially since it was impromptu in a way. It was a very good talk.
Thanks.
Oh, I know this topic.
You do? Oh, look, your name's on it.
All right, so next up we have Jordan Steckloff. And I think this title is the same, yeah. Okay, the survival of amorphous water ice on icy planetesimals.
All right, so let's hope that there's not gonna be any UV. Yeah, wow, these colors are totally different. You guys are right. All right, so what I'm gonna be talking about today is a project that Gal and I have been working on to understand amorphous water ice formation in the early solar system, and more importantly, its survival to the present day. So when we normally think about ice, you take some water, stick it in the freezer, and over time, the water will diffuse into a crystalline structure. The molecules will end up in this typically a hexagonal crystalline shape, and we end up forming a nice piece of crystal water ice. And if it was colder, we can actually get cubic or polycrystalline crystal shapes as well. But this isn't the only structure that water can have. It's possible actually to have water molecules condense into the solid phase faster than the molecules can end up, faster than the molecules can diffuse to the lattice sites. And if this happens, we actually end up forming this free-form structure, this amorphous, well, that's why it's called amorphous water ice, this amorphous structure of the molecules in the water ice. It's effectively a glass. Because this depends, and so we can actually figure out how fast you need to condense water for it to not have time to diffuse into a lattice and form a crystalline structure. And this is a figure from Chesla, 2014. We actually did this exact calculation for both hexagonal water ice and polycrystalline or cubic water ice, plotting the critical flux you need as a function of temperature. And so the idea being that if you are condensing faster than, if you are above these curves, this should be filled in as well, then you are condensing water fast enough that it doesn't have time to form a crystalline structure. And so what's interesting is that if we look at models of the early solar system, during the protosolar nebula, we actually find that for the minimum mass solar nebula model and for some other models that have more mass, we actually find that in regions of the solar system, these curves are in the region where we should be forming amorphous water ice. And so what this suggests then is that even for the minimum mass solar nebula case, we should be forming amorphous water ice in our solar system, which can then aggregate and form larger bodies. So why am I even talking about amorphous water ice? Well, it's thought that the presence of amorphous water ice can be proposed to drive activity in centaurs. And the main reason for this being that it's thought that centaurs, they're too far for the sun generally for water sublimation to be driving their activity, and often CO2 to be driving their activity. You can think of them as being too close for CO to be driving their activity, because if it's CO and there's CO ice on the surface, we should see them active further out, perhaps in the Kuiper belt. And so amorphous water ice has been proposed to be the reason why we see activity at all. And the way this is thought to work is that if we have pure amorphous water ice, it is not in its lowest energy state. It wants to be in a lattice. And so if we could get this water ice to diffuse into a lattice, it releases energy, and a fair bit of it, 2 kilojoules per mole or so, from this figure from Cuchin-Serrano, 2001. And this can be an energy source. Or if amorphous water ice is impure, because when it forms, it can actually trap other volatiles inside, what we find is that if it crystallizes, it can actually push those volatiles out of the amorphous structure, and we can see CO, CO2, and other volatiles being released. So we think that it could either be driving activity or it could be releasing volatiles, maybe not both, depending on the energetics, but that's a different topic. All right, so if we think amorphous water ice formed in the early solar system, and if we think it's driving activity, then maybe we should be able to see it. The problem is it's never been unambiguously detected. And the way you would look for it is crystalline water, ice, and spectroscopists might kill me if I'm wrong on this. That's not my specialty. Is you're looking for this 1.65 micron feature, and really you're looking for the absence of this feature. Crystalline water ice tends to have it. Amorphous water ice does not. So you're looking for the absence of something, which, from what I understand, is a lot more difficult and noisier than you would think. All right, so it formed. It might be driving activity, and we don't see it. So what's going on? And this is where Gail and I have been trying to figure out is if we formed amorphous water ice into the solar system, under what conditions could it survive to the present day, or could it survive to the present day? And so what we're looking at right now is, if we look at the early solar system, this idea that the planets migrated, there were some instabilities, these Mies-style instabilities, where we had an early solar system with nicely orderly planets and this massive Kuiper belt behind it. When the planets went unstable, they excited this Kuiper belt, this proto-Kuiper belt, causing massive collisional evolution of this population before they eventually got scattered out with a remnant Kuiper belt that we see today and the scatter disk and the formation of these other populations. So we wanted to know, can amorphous water ice survive this collisional evolution? And we think this is important because some work from Morbidelli and Rickman showed that these are pretty violent collisions. We're talking a few kilometers per second, and typically, depending on the size frequency distribution of this proto-Kuiper belt, it's likely that very few of these objects were able to escape a catastrophic collision like this. So likely they all hit each other and blew each other apart. So we used the ISAIL shock physics code to study these collisional processes. ISAIL is optimized to study impacts of objects into other objects. So we started off with looking at catastrophic collisions, big things hitting other big things at about 2 kilometers per second. And so if this will play, and so we can, oh, there is a mouse, look at that. Cannot play media, Gal. All right, well, what you would be seeing is a collision plotting temperature on the right, pressure on the left. And these objects, as they collide and merge, you can actually see how the temperature and the shock structure evolves as these objects collide with one another. Now, what we did is take the temperature information from these ISAIL runs, and we ran them through a crystallization model that was originally published from Cucci et al. 1994. Where the timescale of crystallization depends on temperature, and this is largely because this is a diffusive process where if we're really cold, the molecules are not going to move a whole lot, and if we're really warm, they are quite mobile and will move around. And when we put this all together, we can actually look at, if we trace back all of this material to where it was originally in the bodies, we can actually calculate what percentage of this initial material crystallized. And no surprise, right where they contacted each other, it got warm. All of that material is likely went from amorphous water ice to certainly crystalline water ice by the time all was said and done. But the crystallization is largely concentrated near where these two bodies came together, which is quite surprising. We're looking at about 100% crystallization and almost nothing further out. And in fact, we can actually look at, we can aggregate this data and look at what fraction of the total volume was crystallized. And so here we're plotting it as a function of, so between 0 and 10%, 20 to 30%. And what we're finding is a tiny bit of this actually fully crystallized. The vast majority, over 80% of this material was crystallized between 0 to less than 10%. So it's almost purely still amorphous water ice if it were initially amorphous water ice. So what this tells us is that even catastrophic collisions like we would expect during this collisional evolution in the early solar system is not going to destroy amorphous water ice. It can survive to the present day. It can survive this process. Now, we didn't just stop here, because after a catastrophic collision, you would think these objects would reform and form new icy bodies. We also wanted to look at small objects hitting big objects. And this is very common, small things hitting big things. And so we ran the same process, and I'm assuming this movie's not going to play either. But we did the same process where we're tracking how the temperature of this material evolves over time. And if we again trace this back, the material to where it started, we find that very little of it is crystallized again. Up to about 10% of the material in the impactor and in this transient crater might crystallize. But the temperatures are surprisingly low throughout this entire process, such that even if we have a slow speed impact, or sorry, if we have a high speed impact of a small body into a large body, we're not actually going to crystallize a whole lot of amorphous water ice. What we're going to do instead is crystallize a small fraction, leave the interior largely untouched, and the resulting ejecta from this process will start to coat the surface of the body, which means that over time, if we initially had an amorphous water ice in the body, it could still be there. We're just not going to see it because we're forming a crystalline ice mantle on the outside. Now, what's interesting about this process is that even though we're looking at the early solar system, the impact speeds we're studying are actually quite comparable to what we would expect in the present day trans-Neptunian populations. This is a figure from Greenstreet et al. 2015, actually looking at impact speeds for these different populations, cold classicals, the scattered disk, and the other TNO populations. And they're all around 2 kilometers per second or so. This is for Pluto specifically? Yeah. Okay. All right, thanks. So one thing we want to do is actually look at some of these other impact speeds. But for our initial results, we're finding that these results are likely applicable to the present day solar system as well. And what this is telling us then is that amorphous water ice can not only survive collisional evolution early in the solar system, but it can survive collisional evolution in the present day solar system as well. So to summarize, amorphous water ice is able to survive this initial collisional evolution triggered by knee-style instabilities, which suggests that it can survive collisional evolutions of the modern day TNO population. And small impacts wouldn't do really much more than this. They would just they would cause impact gardening that could crystallize the upper layers of an icy planetesimal, producing a veneer of crystalline water ice, such that if amorphous water ice is present, we are not going to see it. But what we still need to do is fully explore the parameter space of impactor sizes, speeds, the effects of porosity in the materials, etc. So now I did not follow Gail's suggestion, including questions here. But since you're my co-author, feel free to pose them to the group. Man, that's how you throw them under the bus. So, and with that, that's all I got. I'll take questions.
Thank you.
So as a contributing author to this specific presentation, and with regards to the last bullet points of the parameter space that involve the sizes, the speeds, and the porosities, there could actually be a very interesting balance there. So if you increase the speeds or increase the sizes, you will increase the energy that you're inputting into the impact. However, if you increase porosity in the target and the impactor, you're actually localizing the effect, and on the overall, you will have less processing of ice. So the interplay between porosity and sizes and speeds will not necessarily act linearly in terms of the resulting amorphous to crystalline fractions that you get.
Yeah, it is really interesting that we don't observe the amorphous ice. I will say real quick that Sarah Greenstreet has a new paper out as well for MU69. And the velocity distribution, a lot of that is due to Pluto's gravity itself.
Okay.
So the velocity distribution is shifted to much lower speeds, which won't change the conclusion on this slide.
No, but it probably helps us out.
Yeah. And the typical is more like 300 meters per second. Oh, and then there's a longer tail out to some, 1 or 2 kilometer per second.
So yeah. Maybe that should probably be something we look at.
And even smaller velocities from there are also expected. Yeah.
Ellen.
Yep.
Is there any known process that can take us in the other direction that can convert crystalline back to amorphous?
Yes.
We'll talk about that, please.
A fair number. So a lot of it all has to do with, can you reprocess ice I think cosmic rays is actually one way to do it when you're really far out. But if you're closer to the sun, sublimation and recondensation on the surface could probably form amorphous water ice under the right conditions.
So what is the time scale for reconversion?
I have not looked at that. Gail, do you have a comment?
So the most prominent process that's been suggested is radiation, turning it back into the more amorphous. It's not completely amorphous as our initial state. It's amorphous-ish because there is still some semi-crystalline structure left in the lattice. And I see Chris Bennett nodding ferociously, which means I'm right.
So I do radiation chemistry, so I guess I should point that out. I'm Chris Bennett at University of Central Florida. So generally what happens with radiation is you can never ever get pure amorphous or pure crystalline. If you start off with pure amorphous, the radiation will give you some crystalline. If you start off with pure crystalline, you'll end up with some amorphous. And so the answer is it's somewhere in between. There's not really a definitive time scale for going one way or the other. It's going to be kind of complicated.
Okay, let me ask a harder question.
Okay.
Should we expect that data analysis should reveal the presence of amorphous water ice on MU69?
Well, that's a loaded question from Alan.
Why don't you repeat the question real quick?
Sorry?
Will you repeat the question real quick for the online?
Oh, yeah. So the question was, the question is effectively, should we then expect to see evidence of amorphous water ice on MU69? If this is the only process that has acted on this object since formation, I would argue yes. If it formed in a region where it should have formed as amorphous and been subject to these types of collisions, then I think it's highly probable and likely that you would have amorphous water ice in the interior. There's a couple of caveats to that, though. There's other processes that can affect the presence of amorphous water ice, thermal heating from the interior, from other objects. It could be that there were so much collisional processing that you might eliminate a lot of it. And it could even be that even if it's present, there might be such a thick mantle on the surface that you wouldn't necessarily see it.
Okay, I think I was misunderstood. Sorry.
Yeah.
I was only trying to pose my question again.
Okay.
Given that radiation processes, like we just discussed, can convert crystalline to amorphous over time, should we expect the surface of MU69 to reveal amorphous water ice owing to that radiation process?
Potentially, yeah. I feel like Gail or Chris could be better answer that question.
So in essence, yes. The problem is, again, we don't have a good handle on the efficiency of producing that fraction of reamorphized water ice. And so I think the problem is twofold. One is just mechanical. If you're coating even a fine layer over that amorphous ice, you're not going to see the signal. You're basically looking at a non-1.65 micron little bump. The other thing is might be spectroscopical. You might be masking or somehow reducing that signal of that specific little bump at 1.65. So you might be producing a masked signal or non-signal.
Yeah. So I guess the trick is, since we're looking for an absence of a spectral signature, if crystalline's there, we might see the bump even if amorphous water ice is mixed in with the material.
I completely agree with what Jordan said. The interior should contain non-negligible amount of amorphous ice.
Right. There's one thing I didn't follow in what you said. You talked about a very thin layer that might be of amorphous ice being created by radiation. It's too thin to really manifest itself in the spectrum. But all of the papers that I have read about cosmic ray deposition in ices show penetration depths of good fractions of a meter to even more than a meter, not just a thin rind on the surface like electrons would produce.
Right.
I was actually just talking about the other way around. So crystalline water ice grains crystalline water ice grains coating over the amorphous water ice. And if the efficiency of the radiation transfer from crystalline to amorphization is much less efficient than the coating of a surface of a small KBO, then what you would more likely see is larger fractional surface areas covered with crystalline water ice signals, more so than any
reformed amorphous ice. That was my answer there. Okay, so just to quickly address that, cosmic rays will penetrate tens of meters down, but when you're out about the Kuiper belt or around there, you actually have like over like the lifetime of say 4 billion years, the solar wind actually contributes a roughly equal amount as the cosmic rays. You could actually have the surface being altered by the solar wind, solar photons, etc. That'd be just on the surface, yeah.
Matthew Knight, University of Maryland. So sort of on a related topic, what about if something were interstellar and traveling from a different solar system? What would you expect as far as re-amorphized? I'd prefer it not to be that, but yes, that idea.
If it's cigar shaped. So if it's interstellar, you're looking at, I would think, cosmic ray processing causing this. Yeah. So I would think that with an interstellar object, you're looking at cosmic rays being your dominant processing mechanism. And so potentially you could form a mixture of crystalline and amorphous water ice in the upper layers to meters to 10 meter scales, the penetration depth of a cosmic ray. But what would that look like? I couldn't necessarily tell you. I would think it would look pretty crystalline, but maybe not purely crystalline. But it would probably be very difficult to detect.
Okay, so this is a question from a non-expert. So are there places where you detect amorphous, for example, fresh surface of comets, or not at all?
From what I understand, go ahead. Yeah. So from what I understand, it's never been detected unambiguously, which means that there have been tentative detections of the absence of this spectroscopic feature, but it hasn't been very clear. There was debate over whether it was seen or not.
And so from my understanding, you're looking at the absence of a feature. So what you're saying is that you always see sort of that feature when you're detecting water. Is that correct?
You can suppress that feature without it being amorphous ice necessarily.
So that's what I was going to say, because
it's also a temperature dependent effect. So sorry, on this screen, it's a little difficult to see. Online, it's probably a lot clearer. But we're actually plotting 3 different, Leto et al. Actually plotted 3 different temperatures, 16 Kelvin, 110 Kelvin, and 150 Kelvin. And it's at the coldest side. Actually, at this point, I can't even tell which one shows it. Some temperatures, you actually see this feature much more clearly than others. It is a temperature dependent effect.
I see, because I'm thinking like some features, spectral features, just get completely attenuated by the fact that you have small grains on the surface. So if you had your amorphous, so a flat spectrum could also just be, fine grains of crystalline water ice. Is that correct? So it's difficult. Is like non. Okay. All right. Yeah. Okay. Thanks. That was just
All right. If there's no more directly for Jordan, we can go to the general discussion. And you can still have questions for Jordan, but you could also have questions for Matthew or anyone in the room. I think, do we still have, let's see here, Rosita online? I didn't look at the participants list, but we can see if she's still online if you have questions for her. Matthew has a question for himself. No, just kidding. Here you go.
Well, it's a question I thought of during Rosita's, and if she's here, I'd love to hear her thoughts. And if not, we can just talk about it in the room. But so when Rosita was talking about the surface shape transitioning from the high cliffs to boulder type things, I was trying to think, and then thinking about MU69, where I don't think there is evidence of large cliffs, but I could be mistaken on that. I'll finish my question, then Kelsey may start responding. But I was trying to think if there's a mechanism that might cause the high cliffs during the Centaur stage, and maybe it's outbursts, whether it's from amorphous to crystalline ice transitions or something else. If there's a violent outburst and then a subsequent collapse, maybe that might give you this large terrain variations.
So I do see Rosita still online.
Yeah.
And also it's funny because Daniel and I were just discussing that same thing, is that you have to be careful, a little bit careful about lighting geometries and how topography appears. But in general, we don't see a lot of sharp cliffs or features like that. And I was thinking the same thing, is that I always consider those to be an evolutionary feature, but maybe it's, one step in the process, and going down the line is where you get to what Rosita was talking about. Yeah, Rosita, if you want to say something too, and did you want to say something, Daniel? Yeah.
I would just say, I have a quick comment on that, actually. It's really just plugging Taylor Safford's talk later. Because you were talking about, like, is this primordial or is it evolutionary? Because they'll be saying that on the one hand, the formation of topography could be evolutionary. And then on the other hand, the loss of topography could be evolutionary. And I actually think both could be correct, where certain processes that are active can actually form topography in different types of shapes. And then different processes that are active later on in the evolutionary process actually can flatten them out again. Taylor's going to talk a little bit about the formation of interesting shapes in the Centaur region due to processes that are active there. So,
yeah.
Not to put
if I may add something.
Go for it.
Yeah. So it's, when we're looking at 69, we're looking at an object from the cold classicals, and the scattered disk objects might have been exposed to more collisions in the very early solar system. And there is a team working on this topic around JB Vincent. So they're trying to understand the collisional evolution in the early solar system, and they're trying to see whether they can reproduce some record of pits that could correspond to what we observe on 67P. I don't know if they have any conclusions yet, but they're definitely working on this to try to understand whether this happened in the early solar system or it's an effect that occurred later.
Great, thanks for bringing that up. And we can also see you, so we should, cameras behind us, we can like wave.
Hi.
Sorry, what did you say, Maria? Can you repeat the team that's working on that?
Jean-Baptiste Vincent. So they have an EC international team. So this is funded by the International Space Science Institute, if I'm not wrong, in Bern. So they have a group of about 10 people trying to understand that.
Great, thank you. Anyone else?
I actually have a discussion question.
Yeah.
So my discussion question has to do with, I think, parts of what Matthew was showing in his talk, and it's related to surface evolution that Rosita talked about, and to some extent the drivers of the surface evolution. I know it sounds like a dumb question, but what is an outburst? So when we look at 29P Schwarzmann-Bachmann 1, outbursts can be a 3 magnitude increase, or they can be a 7 or 8 magnitude increase. It's a huge range. Before the 9P Temple 1 observing campaign, Temple 1 was an active comet, but then during the observing campaign, it had a lot of very small, sort of kind of diffusive features all along. Same thing with a much higher degree of resolution for 67P, Churyumov-Gerasimenko. It's kind of active at different sites on different times of the diurnal or seasonal time scales. And so when we talk about centaurs and when we want to talk about triggering or characterization of outburst and its drivers, my question is, what is an outburst? And Mike Kelly is going to answer that question.
No, I am not. Thank you. Yeah, Mike Kelly, University of Maryland. First problem with just the language of outbursts is the magnitude system. I mean, that's just the problem with astronomy, right? Yeah, it's also a great benefit. Yeah, so delta magnitude of 5 for Schwarzmann-Bachmann 1, since it's an intrinsically 14th magnitude comet, it means something different for Total Giacobini-Kresák when it's a I don't know, 7th magnitude comet. And then there's that whole distance thing that, okay, but anyway, I think, yeah, so first thing that some people have done, like Masataro Ishiguro in his paper in 2016, I think it was sort of studying Comet Finlay's outburst, but kind of aggregated a bunch of other ones, is to turn it into either a cross-section, a total cross-section, or a total mass kind of thing. And I think we're talking about order of magnitude, and I'm going to talk in volume space, which is already a problem again. Meter-sized regions being ejected, or maybe tens of meter-sized regions. So feel free to correct me, but first of all, yeah, that's about the size scale I think we're considering for most outbursts, most of the ones that we know of. Yeah.
What happens if you're an object that regularly 7, 8, 9 times a year throws out an equivalent of a meter scale relative to an object that does it only once in its orbit? Which one would you characterize as a major outburst, a minor outburst, continuous activity? There's also the temporal scale for that, which again, we don't know very well because that folds into the issue of the dependence on rotation, the dependence of the drivers of activity, etc. So I don't have the answer, just a question.
Is this one on too? Okay.
Okay.
A little less passing.
Okay. Thanks. Henry Shea, Planetary Science Institute. I mean, I think the answer is just we should look at them all, right? Like, I mean, there will be major outbursts and minor outbursts, and they're both probably important to understand. And actually, I was going to make this comment earlier, but there's like a good segue. I was going to say this at the end of Matthew's talk, but like, and I have a feeling it'll come up a lot later on. But like, so you've talked about follow-up of LSST observations, and there's this paper that came out a couple years ago, probably only on AstroPH and the LSST website, so probably not many people have read it. It was also really long, but it was basically a study of the follow-up requirements in the LSST era. And there was 6 different science areas that were considered. And basically each science area can use 100% or 500% of the world's assets, just for that science area. So, and probably, so there's a lot of complications that will arise with follow-up in the LSST era. There will probably need to be prioritizing of follow-up opportunities. There will probably need to be data sharing for the entire community, potentially, when it comes to public facilities, at least. So, so something I think maybe for us to consider here is what are priorities for the Centaur, people interested in Centaurs, do we just want to chase the brightest outbursts, or do we want to chase a range of outbursts? I think we should chase a range of outbursts. And how many outbursts do we want? When it comes to prioritizing things that we want spectroscopy of, or things that we want deep imaging of, yeah, I think that's something I feel like will be a running theme, and probably something that we should include in our final white paper, for instance. What?
Excellent lead-in.
Okay, great. Okay.
Keep going. But I guess would it be correct to title this more like observational priorities?
Sure. Yeah.
What you're discussing. So we can just, for the white paper, we could start making a list. I'm sure other people have typed some notes, but just for our record here, we know what we've captured. What are the ones you already said?
I think we should chase a range of outbursts, a range of outburst intensities.
Okay.
And maybe we should think about how many of each, category. Well, yeah, so defining categories might be something to do.
What are even the categories?
Like what Gal said, repeated outbursts, small outbursts, big outbursts.
Yeah, so in the last DPS, my talk about 29 PSW1 encountered that problem. There were several papers that tried to somewhat taxonomize the outburst activity for 29P. And then you encounter what do you count as a major outburst? What do you count as a minor outburst? How many of them happen at what repetition? And that folds into the understanding or interpretation of the rotation period, of the different physical properties of the nucleus of 29P Schwarzmann-Bachmann 1. And so I think that together with the observations, the priorities for observations, we can also make a point of trying to at least raise arguments as to what would the distribution of outbursts, what can a distribution of outbursts tell us in terms of the physical behavior of the object, and how can we, is there any sense in discerning, small, medium, large, tall, grande, venti outbursts for centaurs?
I guess this is Jan Fernandez for UCF. I guess I was just going to add in terms of categories, I guess there's some evidence that there are gassy outbursts and dusty outbursts. And so that aspect, I think, is very interesting. That might be giving us some important clues. And so we want to be ready to not just see the dusty ones, which I guess easier in general to get, but if we get gassy outbursts too, that would be spiffy.
We do have a second one.
Walt Harris, University of Arizona. I think another thing that we really want to get for outbursts is to classify them by event duration and energy balance for the observed material. So if we know how long it took, we can measure the AFRO of dust that comes out, measure the gas species. That tells us how much kinetic energy went into what was being outbursted. And that can be related, given the heliocentric distance, to how much energy could be delivered to different areas on the surface.
Thanks. We do have a question online too, so let's do Alan and then we'll do the one online.
Yeah, for Jan, do the dusty and gassy outbursts, are they seen on the same objects or different objects?
Maria can answer that. Well, I know there are on.
We will get to your online question shortly.
I think I saw some gassier and dustier. Okay, definitely. Yeah, I'm talking about this.
We, in fact, I don't know if Casper is online, but I'm talking about his data that he has for 29P. So we see evidence for that. Yeah.
And they're separated enough for us to, to confuse us enough about what is the actual physical process that produces this lag between them.
We see outbursts in the CO gas and outbursts in the dust that are separated in time enough that are confusing to us. Not necessarily. Maybe.
Until you suggested correlation, I was thinking about two different mechanisms.
Yeah, they could be. Again, initially we thought they might happen at the same time, but we're not necessarily seeing that in the data.
Delay time scale, which one leads?
We don't know. We don't have that. I'm sorry, what?
Repeat the question if you can.
Oh, the question was, what is the delay time in the outburst of the gas and the dust, or vice versa? And we can't say that yet. We don't have enough data to say that yet. No, okay, we don't know which one leads. The separation that we're seeing is on the order, I don't know, 10 days to 2 weeks. Yeah, see what I mean about confusing? Yeah, well, yeah. So, all right, so we had a question online.
Yeah, quick question from Michelle Bannister. Do we want spectroscopy on all outbursts?
Of course.
I'll add spectroscopy to the list that we're writing.
Spectroscopy would be fantastic. Yes.
Thank you, Michelle.
Yeah. Thanks, Michelle, for raising that point. That is really important.
I'm just curious, we're talking about LSST here, but ZTF is on Sky right now. Is the Centaur community plugged into ZTF?
there is some ongoing work with analyzing the ZTF, using it as a way of monitoring outbursts with centaurs. Yeah, okay.
Yeah, follow up from Michelle. I've been asking the multi-fiber surveys if they can watch everything for us. In other words, MSE and moons. Sure. I've been asking the multi-fiber surveys if they can watch everything for us. In other words, MSE and moons. MSE, I don't.
Michelle, what does
yeah. Do you want to clarify
MSC
that?
stand for?
We can have her.
Do you have a microphone?
Yeah,
You
she
could
says if
actually
that
speak
interests you, chat. Oh, yeah, she can take the mic. Hold on one second. Michelle, let's get you unmuted. Hold on one second.
Let's get Michelle unmuted and she can actually talk.
Okay, you're good.
Hi folks, so MSC is the Mauna Kea Spectroscopic Explorer and, affiliation, Queen's University, Belfast. The Mauna Kea Spectroscopic Explorer is a concept to replace Canada France Hawaii telescope in the same dome volume with a dedicated 10-meter multi-fiber spectroscopic setup. So at the moment we're discussing with them if their engineering requirements can accommodate basically providing low-res spectra, where low-res would be higher than we normally think about for everything that comes through their field of view. So moons is probably technically more challenged in providing this kind of thing because the ESO scheduling requirements are likely to be a little bit more constraining on them, but both are interested in pursuing this sort of science case.
But first light in 2026.
The concept.
Yeah. Okay. They just had a design review.
Thank you, Michelle.
This is Henry Shea, PSI. Is it good? Okay. Just to kind of follow up on the LSST and ZTF follow-up topic, like some of us are working on this too, but something else to think about in addition to what our priorities are what those things might look like in ZTF or LSST data. Like Mike was saying, what will our actual trigger conditions be for, objects of different magnitudes or different ambient activity levels. But also, I was asking Jan separately about the dusty versus gassy outbursts. Like, what would we look for in LSST data if we want to say, trigger on 5 dusty and 5 gassy things? How do we know from the LSST data alone, how do we, identify things? And so they're so that's like getting down to the actual specifics of not just what do we want to trigger on, but how are we going to trigger, what conditions are we going to set for those triggers? So
this is Matthew Knight, University of Maryland. I just stole Gerbs' response, but so Henry, I would say if these have the same gas species that we see in comets, then you can do this potentially with colors. So, for instance, if there's a lot of C2, you might see the green, it might look greener or bluer, more brightening in G than R, as opposed to something that was dusty where you might see a similar brightening in both filters.
And just to point out that I'm just going to go in that direction, but they, as in Matthew's talk, there was an example of outbursts with ZTF with Echecluse that was observed. That was actually a contribution to the paper that we made, so I think the question then becomes, what is the sensitivity of the magnitude that you can actually detect with whatever you're using in terms of of the outburst. If you want to get all of every outburst that you can get, right, you're limited basically by your sensitivity of your survey or whatever your monitoring tool is.
This is Jan Fernandez, UCF. I guess I was just going to pose the question, like when you mentioned the colors, that seems like a sufficiently easy experiment to do. Has anybody, I mean, GURBS has got a lot of broadband color data on centaurs, right? From ages and ages, right? And a lot of people have that, but has anybody actually gone through and said like, oh, wait a minute, this object was greener here than it was here? I guess, it's a really honest question. I don't know the literature well enough to say like, oh, someone has actually gone through and checked the broadband colors, which, like I said, would be an easy thing to do, to be sure if that's.
I actually have it's a dumb question, maybe for non-broadband photometry observers like me or at all. How much C2 will you expect to be contributing at a Centaur distance versus a JFC distance? It's a daughter product. Yeah. So you're not going to have the same efficiency of producing.
Yeah. Well, I mean, no one's been. Correct me if I'm wrong. No one's seen C2 specifically identified C2. Right, but CN has been seen, right? So you could, it doesn't have to be greener. It could be if it's bluer.
Right,
right?
But yeah. I mean, it's bluer in what is the production of this daughter product at these distances at perhaps more diffuse coma, at least inner comas.
Someone could do the calculation.
Right.
Do the calculation, so you get 10 to the blah 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 multiple per second, CN, boom, figure it out. Yeah. You do 10 to the 25, 10 to the 26 production rate of CN or whatever, and say like, oh, it's going to boost my signal in the right broadband in B band, I guess, right? In B band, yeah, by so and so many mags, and see what happens. Yeah, I don't know.
So just in terms of the color during outburst and during activity, there's been some work with Chiron. There's been some work in the Jewett 2009 paper trying to track the colors, but there's, in terms of definitive correlations, not much. The thing that I think in kind of a broad brush sense, right, these tend to look neutral when they are right. When they're and so if there's no dramatic V minus R or broadband correlation.
And right, and it takes a little bit of work to get a color plus or minus 0.01 and something like that, right? Yeah. So it's not trivial, but you got it doable, but not trivial.
And I was just going to add something. One of the reasons Casper is not here is he's doing an industrial practicum at Catalina Sky Survey. And one of the things he's going to do is go through, data mine through their data, look for contributions from a range of objects, including centaurs. So stay tuned. Got to work cut out for himself.
It's almost lunchtime.
Oh. Right. Any more questions from maybe people online? You can be unmuted and then be featured on the big screen.
So far, I don't see any either.
Okay. So if you don't have any more questions in the room, we can